All right, so we're moving on to these rotational dynamics posters. Remember, again, bring in a laptop tomorrow because I'm going to open up a multiple choice set in the morning, right? And then we'll go over the questions for the rest of the week. Okay. Get enough RQ at some point too. All right. So unit 7, remember this was rotational dynamics, which was pretty hefty unit. Oh, I want to mention too a couple of questions you guys are going to see tomorrow. I did pull from unit 3, which is like centripetal force. So there's a couple of questions like centripetal force, but I thought it'd be good to throw in here too. Right. Here's the kinematics, right? The rotational kinematics. You guys remember those 3 kinematic formulas from? Okay, let's look at the linear version of these, right? Like x equals v naught t plus half at squared, and the other two. Right? Here's those, right? Well, if you look on a turntable, and instead of linear displacement in meters, now you have angular displacement in, say, like radians, right? And then here's angular velocity instead of linear velocity. Here's angular acceleration instead of linear acceleration. So this would be like speeding up or slowing down a turntable, something like that, right? Oh, I have a turntable in the next one. Maybe let's get a picture side by side, right? And so these kinematic relationships also work. Now, remember, though, everything has to be in terms of radians. So like you could measure angular displacement. That's what theta could be, like in degrees. Like that is measurable. You've got like what this terms like 90 degrees, right? But you can't put the number 90 into these equations, right? You have to convert that into radians first. Right? So you guys remember about that? Right. Then just like the kinematic, the linear motion version of this, if you can identify any 3 of these, you can, in principle, solve the other 2. Right? Like if you have a turntable and you have it spinning at so many radians per second, and then it slows to a stop in like 5 seconds. It's like, okay, well, it slows to a stop in 5 seconds. I know final velocity is 0 radians per second. I was told how fast it was initially rotating. I told how long it takes to come to a stop, right? So I could solve for what's the rate that it's slowing down. That's alpha. And then once you have that, okay, now you know all 4 of these. Now you can go figure out, well, hey, I wonder how far did it turn during the whole process, right? You see the big picture, how you can navigate that, right? You got like a forest for the trees view right here of that, any kinematic question, right? So here we go, turntable. Now you can translate back and forth between linear and angular motion by multiplying or dividing by your location from the center R, right? So suppose you got 3 kids on a merry-go-round and we're up in a helicopter, looking straight down these 3 kids on a merry-go-round. They're whoa, they're all getting dizzy. Right? So like, how far did each kid move in like meters, right? Well, you have to multiply 2 things together, right? How far did this whole merry-go-round turn? But also, where was the kid sitting? Because if he's sitting right at the center, he hasn't actually moved anywhere, right? He's just spinning, right? But then further out, there's like larger circumference, right? In fact, a specific version of this could be circumference equals 2 pi r, right? And then here's the more general version, x equals theta r. I guess that also follows for speed and acceleration, right? So you can go back and forth there. Right? Now, one of my posters hanging up that I don't know, seems like it went missing somewhere, is the version of the turntable slows to a stop. But I do have this linear motion version of car brakes to stop. So this is way back from unit 1. You guys remember car brakes to stop? X versus T, V versus T, A versus T, right? Now, if you change this to this turntable slows to a stop, and you just replace this with theta versus T, omega versus T, alpha versus T, it would be the exact same graph shapes, wouldn't it? Right, exact same graph shapes, right? That'd be true. Right. So hopefully, like if I gave you blank sets of axes and I gave you that scenario, something like slows to a stop, you could come up. It might throw in the word uniformly, right? Like a constant acceleration. Right? Hopefully, you could come up with those like from scratch. Right. Right, rotational analogs. So everything we had in linear motion, we've got this rotational version of it. Now time in seconds is still time in seconds, so that one's the same, right? Instead of saying how far in meters, now we're saying how far something turned. And for the calculations, it's best to stick in radians if you're applying formulas, right? Anything outside of sine or cosine, right, has to be in radians, right? Instead of how fast, like miles per hour or meters per second, now we're interested in like a turntable rotating, right? How many radians per second? For example, the Earth makes 1 rotation every 24 hours. That's a version of this omega, right? You can quantify radians per second, right? Instead of a car speeding up or slowing down, like breaking to a stop, maybe, right? Maybe you can have like a turntable speeding up or slowing down this rotation. It's some change in radians per second per passing second. Okay? All right. So the top half of this table is like rotational kinematics. That's what we've been looking at last few posters, right? But the bottom half of this table we really didn't talk about until December. Right? So this is bringing the dynamics part of this. Now, mass for the first few months in this class, back in like August, September, October, November, measured how much inertia. So you push on a mass with a force, it's going to accelerate. How much does it accelerate? Well, that's inversely proportional to the mass, right? The more mass, the less it wants to accelerate for some force, right? But when you get to rotation, let's say like I wanted to rotate this or roll it, right? Now it's not just how much mass, but it's how is the mass distributed. So it's the sum of mr squared, right? And well, come on pretty soon. Right. You guys remember this whole rotational inertia table? Right. So for a single point mass, it could be mr squared. If I have 2-point masses, mr squared plus mr squared goes 2mr squared or something like that, right? But what if you have like a whole like disk rotating or a ring rolling or basketball spinning, right? Now, you will not be expected to memorize the values from that rotational inertia table. If AP wants you to apply anything, they would give you the expression. So they might say like, oh, there's a basketball spinning about its central axis, and they would tell you I equals 2/3 mr squared for that particular case. Okay. Right. Now you would have to be able to apply it though. Right. All right. So how could you possibly apply this? Well, instead of forces causing masses to accelerate, now you're gonna have torques that cause, say, like a turntable to rotate, or maybe like opening a door, right? So torque is R cross F, but that's also I times alpha. I've got some posters for that, so when you see that coming up, right? There's momentum. Now, instead of linear momentum being mass times velocity, we got angular momentum is I times omega. It's just the analogous parts plugged in, right? Instead of M, it's I. Instead of V, it's omega. All plugs in. Right? There's also this rotational kinetic energy. So linear kinetic energy with 1/2 m squared. Rotational kinetic energy, so there's a ball rolling across the floor. So I'm gonna do with 1/2 I omega squared. Okay. Right. So you guys remember all that? Okay. All right. Let's look at just one real fast. Center of mass. AP is gonna ask you a center mass question, but they probably won't ask you to do this type calculation. AP likes to keep center mass questions like conceptual. A lot of times it involves some kind of collision, and they just want you to recognize that the center mass doesn't change given some collision. Like if you've got two objects colliding, the center mass before and after the collision just keeps on doing whatever it's doing, kind of thing. That's usually how AP asks that type of question. Right. Okay. Rotational inertia. So you guys remember these 2 meter sticks? It's still got over here, these 2 meter sticks, and I just tape the weights on in different parts, and you shake it back and forth. Right. Now they're the same mass and the same weight, but the distribution is different. So if you like slide the masses out like 3 times as far, 3 times as far squared, that's 9 times as much. Oh, what's 18 compared to 2? Oh, that's 9 times as much. Like I said, right? So mr squared, you sum up all the little bits. Right. Here's the full rotational inertia table for these different shapes we're just looking at. Okay. Torque. Torque, we got R cross F. So think a wrench trying to turn this rusty nut. Right. So here's your lever arm R, here's some force F, and the cross product means you only care about the perpendicular components, right? So if there's some angle theta, you have to consider that too. You might do like RF sine theta if they give you this theta. Now, if they give you this theta here, deviating from the perpendicular line, then is this sine or cosine? Let me see, show hands. How many guys say it would still be sine? How many say no, it would have to be cosine? Yeah, right. That's if they give you this angle rather than this angle, right? If they say the angle deviating from the perpendicular is turns of cosine. Okay, so be careful about what angle you're given, right? And then the other perspective of torque is that it causes some inertia, some rotational inertia, to accelerate in an angular sense. This is like speeding up spinning if you're still applying the torque. Right? Do I have? I'm thinking more like we go way in the future. Where's that poster? I know I'm thinking of one. Where is it? Ah, this one way over here. Right. So this comes back. It's going to come back later in class. Right? So as you wind a string around a turntable and pull with some force, now that force is some radial arm that's causing a torque. Right. And that torque is causing this turntable to speed up spinning, hence alpha. Right. Okay. All right. Equilibrium. So the first version of equilibrium you guys learned probably in October or so is that the sum of the forces goes to 0, and that's true along each axis. So if you split some force into components, right, you could go 2 dimensions, you could go 3 dimensions, the forces have sum 0, right? Then in December, we introduced the final condition for a true equilibrium, which is that the torque also zeroes out, right? So it's not just the forces zero out, but the torque also zeroes out, right? If you go to engineering school, you're definitely going to see, well, I guess a lot of this class, but especially these come back, right? So, right. And the versions of this we did in class, I had you guys do a 2-part lab involving a torque equilibrium, right? So one version was like this, like seesaw. So what if you have like a meter stick sitting on a pivot point and you have a couple of weights on it, right? And what you can say is that the R cross F, try and make it go counterclockwise, has to balance out with the R cross F, make it go clockwise, has to zero out, right? So I gave you guys a simple example here, right? If it's 3 times the weight, then it has to be 1/3 the distance from the pivot point, right? Now that's summing the torque from this pivot point, which is probably the most intuitive way to do it, and probably how AP would frame it too, right? If you want a bigger picture of what you can do, you can actually pick any point and sum the torque about it. You could pick this random point right here and sum the torque about it, and it would still zero out. Right? So probably that pivot point right there is the most intuitive point, right? There's a lot of table you guys did for that. Right, you do like that. Right. You can use it. One way you can do, one purpose you can use this for is you can find unknown weights, right? This is the principle of the triple beam balance. Is there's like some preloaded weights on the balance, right? And then you take something of unknown mass, unknown weight, and stack it, right? And then you slide the masses around until it restores balance, right? So that's the principle of triple beam balance right there, right? And now the other version of this was the scaffold version. I think I need to go back and retitle this scaffold, right? So suppose you have this the scaffold held up by a couple of cables, and you're walking back and forth along it, right? As you walk closer to the right, the tension on the right increases and the tension on the left decreases, so that you're looking for 2 conditions. One is that the sum of the forces goes to 0. In this case, all the forces are vertical. So these 2 upward verticals balance with these 2 downward verticals, right? So it zeroes out, right, in terms of force. And the other condition is that the torque zeroes out, right? And you can't solve the full problem, like what are these 2 tensions, without both of those details. Again, because depending on where you're standing, like if you stand on the left versus stand on the right, the force equation would look the same either way, right? But the torque equation would change because your location would change, right? And therefore these individual tensions would change. Okay. So, right, you guys get there? No? Let's do one. Let's do one of these. Okay. So I think we got time. Let's see if we do. Throw you guys a specific problem. Let's say we got a beam with length equal to 10 meters. All right, got a 10-meter long beam. And let's say this beam weighs 80 newtons. So I'll say the weight of the beam is 80 newtons. Okay. And let's have a guy standing right here. Right. Let's say at the if this is 0.8 or sorry 0.0 meters, let's call this 8.0 meters. Let's call this 10.0 meters. Right. Let's say this guy weighs 600 newtons. So has a weight of the person is 600 newtons. Right. Let's get a couple of cables. I'll call this tension on the right and tension on the left. Tension right, tension left. Okay. Right, you guys see that? Okay. So it's made that up from scratch on the fly right here. Right, you guys solve it. I'll solve it. The question is, what are the 2 tensions? What is this tension on the right side? What is this tension in the cable on the left side? Right, the right cable and the left cable. Right, you guys solve it. I'll solve it. Let's see if we get the same answers. All right. I've got it, and I checked my work and tried 2 different ways. I'm getting the same answer both ways. Right. So let's see. Who knows? Who knows right now? What are the two tensions? What are the two tensions? Who knows? Who knows? All right. Keep working on it then. Trying to figure out what are those two tensions. How about now? Who knows now? Yeah. What you got? 540 for the right and 160. All right, that's what I got too. I got 520 newtons. Here, I'll just give you guys the answers here. All right, so 520 newtons and 160 newtons. Exactly what I got. All right, so how would you figure that out? All right, so I have to pick a point as a pivot point. Now I'm going to pick the 0 mark as the pivot point. Right here's why. Right, because my two unknown forces. Well, one of them is at that point. So if I treat that like the door hinge, if you press on the door hinge, that provides no torque itself. So if I set up a torque equation, I've eliminated one of my unknowns. Therefore, I can immediately solve for the other one. Okay? So if I treat this as the pivot, little quote marks, right? Then the weight of the beam here at the 5-meter mark, the center mass, is causing a clockwise torque. This guy standing here is causing a even larger clockwise torque. He weighs more and he's further out. So both those reasons, right? And this tension on the right is holding everything back in check. That's counterclockwise. That's 3 torques. I see this torque, and this torque have to zero out. The sum of the torque has to be 0, and then Newton meters for a unit, right? Okay. Right. Now, I know that torque is R cross F. So let's do 5 meters crossed with 80 newtons. 5 meters, 80 newtons. Right. Now that's clockwise. Traditionally, you call it clockwise negative. So I'll just go ahead and throw a negative sign in there. Right. Here's another clockwise queued up. So I'll say also minus. I got 8 meters. This guy is 600 newtons weight. Right. And then I'll say plus because I got a counterclockwise coming in. So plus at the full 10 meters is some mystery tension on the right side. Okay. I know that all has to collectively sum to 0. So all this has to sum to 0 Newton meters. Okay, like that. All right. So let's see, what's 5 times 80 plus 8 times 600. Right. Then I'll add that over to the other side. Then divide by 10 meters. Tension right is 520 newtons. Okay, so there's the right side. Okay. Okay. Now, how do you get the left side? Well, here's a couple ways you could do it. One way is you could just pick another random point and sum the torque about it and zero it out and solve for the tension left, right? But the other way you could do it is, well, I remember a force equilibrium. I remember the sum of the forces have to zero out, so 0 newtons. So I've got 2 upward forces and 2 downward forces that have to zero out. Well, my 2 downward forces are 600 newtons and 80 newtons. So there's a total of 680 being pulled down. So 680 is being pulled down, right? Oh, I've got 520 pulling up, so I'll subtract that. And then that difference, as soon as I hit enter, tells me what the left tension must be to restore balance so that everything zeroes out. Okay? And that is up 160 newtons. It's another way to do it. Okay. All right, guys, good? All right, guys, let's solve the scaffold. All right. All right, and then yeah, you guys also did a lab version of that too, right? How'd you guys see that? Oh yeah, the torque zeroes out, and you can solve for like unknown forces, something like that. Okay, all right, guys, good so far. All right, now, right hand rule. AP is not going to ask about this year, but they will start asking next year. So maybe you're gonna be familiar with this. See this in college. Okay, AP is when you guys take the exam, they're always going to frame torque in terms of clockwise or counterclockwise, right? But if you think about it, if you're standing in front of it or behind it, then that definition changes, right? It flips. So there is a more universal 3D way to think of it, and that's to open up a z-axis. So if you have like an XY plane for your actual torque, right? You can define torque along the z-axis, right? Use this right-hand rule to define is it like positive z-axis or negative z-axis, right? Clockwise or counterclockwise, right? So you might see that in college, right? Right. Same thing with parallel axis theorem. AP is not going to ask about that this year, but I've heard they're going to ask it starting next year. Right? So if you have a ball rolling on the floor, then it's not just rotating about its own center, like if it was spinning on your finger, in which case for basketball, it'd be 2/3 mr squared. Right? But also you have to say the axis it's rotating about is actually offset from that table value. So you add m times d squared. In this case, the ball rolling on the floor, the distance would be its own radius. Right? So you get a different rotational inertia. Okay. Right. So good to know there. You guys remember doing this lab? Okay. So this combines a bunch of parts, right? Is you wind a string around central axis, right? You drop a weight, let it go, right? And this weight's going to slowly accelerate, which is going to cause this to also accelerate. It's going to undergo an angular acceleration. Okay? And ultimately, you can calculate what is the rotational inertia of this crazy shape, right, about the central axis. Right? So maybe I should move this back a little bit. Right? It's kind of this principle here. Is torque is r cross f, so r cross f, but it's also I times alpha. Now there's a little bit more to it because this falling weight, you had to consider that the tension was a little bit. Here, see if you guys remember this. Let me ask you guys instead of just saying it. Right, guys, when this weight is falling, how does this weight mg compare to the tension in the string that's providing the force, therefore torque for this to rotate? Right, this weight compared to this tension, are they the same? Yes or no? No, they're not exactly the same. Right, now if it's slowly accelerating, it'll be pretty close. Right, but which one's a little bit bigger? This weight or this tension? The weight is a little bit bigger. Like if this weighs 10 newtons, suppose you throw this on here, 10 newtons, okay? Maybe this tension might be like 9 or 9.5 newtons or something like that, right? We're talking about elevator physics, right? Would it be like a downward accelerating elevator? It might be slowly accelerating, but there would be a net force that's not zero, right? Okay. So that was a little part of it too. A little bit of elevator physics. M times G minus A is the tension force. Like, a lot of parts we were juggling there. Angular momentum, here's a new concept. So a classic example of conservation of angular momentum is the figure skater. Remember, regular linear momentum was mass times velocity. The rotational version of that got capital L instead of lowercase p. We got capital L. That's I times omega. Instead of mv, it's I omega. Right? So we got rotational inertia times angular velocity. And remember, that property is conserved in closed systems. So that's what this box says here. The sum of angular momentum before and after some event, right? Usually looking for some kind of collision. In this case, the ice skater pulls their arms in, is going to speed up spinning. Right, but you can show that the angular momentum is the same before and after. Okay, right. So you guys remember that angular momentum, right? You know what a question AP likes to ask too? I bet you're going to get one of these questions: is angular momentum for a point mass? So what if you have like a ball of clay that sticks against the swivel stick that's pivoting about this point? So throw it, and then starts to rotate, something like that. Right? AP likes this question. You're going to get one of these. Right? So, like, what's the rotational moment? What's the angular momentum associated with like a point mass? How does that make any sense? Right? So, I think of one of the homework solution sets. I did derive this for you guys, but so you just take it as mv times r. So mv is just the plain linear momentum, right? If you multiply by this distance r, like this radial arm, that'll tell you the angular momentum associated with point mass, right? There's maybe one more detail I should throw in here too, which is, did you guys see how this is being thrown in perpendicular to this radial arm, perpendicular, right? If it was at any other angle, you'd have to throw in either a sine or a cosine, depending on what angle you were given, right? Sometimes this is written as r cross mv, right? R cross mv, okay? Right. And then you can figure out like what's the angular momentum after, which is just mvr, which is therefore, then you can solve for angular velocity, right? If you know what is I. Right? All right, here's a good classic setup to have in your mind is got a turntable, got a string wound around this turntable, and we're going to pull with some force at some radial arm, which provides some torque, which is going to cause that turntable to speed up spinning. Right? At the same time, it's increasing its angular momentum. because for a constant torque and a constant rotational inertia, you would also have a constant angular acceleration, which means that your angular velocity is always changing, right? It's changing at a constant rate for a constant angular acceleration. Right? You guys remember the two? Right? So got r cross f equals I times alpha. It helps set that up, right? And then maybe you can go back to kinematic motion. Let's look at the very first poster that opened up today. Right? You say something like maybe it's accelerating for some amount of time, or how about this? Maybe it's accelerating for some number of turns, some number of radians. Right? You can figure out how fast is it rotating after that particular interval. Right? And then you can figure out what is the angular momentum. Right? And a couple of graphs side by side that could apply to that scenario. Hey, guys, keep this picture in your mind as you're looking at these pair of graphs right here. This pair of graphs, okay, is again, just follow exactly that story, that example I just gave you. If you apply a constant torque, maybe for some time interval, right? Hey, that's what this graph on the left is showing. It's showing a constant torque, right? You guys see like a constant value for torque, right? Constant force for a constant radial arm. That's a constant torque, right? But that's going to cause the turntable to speed up spinning. Suppose it starts from rest, right? Maybe start with 0 angular momentum at time 0, but it's going to increase angular momentum at a constant rate, right? Now these two graphs are related to each other. Like if you know one, you can know the other, right? They actually have a calculus relationship with each other. You guys see, well, if you're in calculus, you can say like the integral under torque versus time tells you the change in angular momentum, right? And then you can say the derivative, the slope of angular momentum versus time. Well, that tells you the torque, right? So these are like two sides of the same coin, right? You can go from one to the other. Right? And sometimes AP might throw you a little bit curveball version of this scenario. I say, what if you have a variable torque? They could throw that at you, right? Which I didn't make a poster for, but they could. I've seen them ask that question. Because what if you have a variable torque? What if there's a torque that looks like some kind of linear relationship like this, right? If you saw that, then what would L versus T look like? It would no longer be a straight line. It would be a what? Parabola. Yeah, it would be a parabola like that, right? So if this was a linear relationship, torque versus time, then L versus T would be a parabola. Okay, all right. Yeah, I've seen AP do that before, so they might do that. Okay. Ooh, spinning the basketball. So you got the basketball on your finger, you bam, give it a bump, some force for some maybe tiny time interval. How fast is it now spinning, right, as a result of that? Right. So this is going to connect torque to angular momentum also, right? So torque times time is a change in angular momentum, right? That's what we were just looking at. That's what this graph says right here, right? So some constant torque for some time interval. Hey, got a rectangle shape. So the area of a rectangle is just base times height. That's exactly what that's saying. It's a little equation form, right? Same thing. Right. And then, okay, I know torque is r cross f. So this basketball has some radius. I just, bam, bumped it with some force. I guess a friction force is what that would be, right? Like, bam, there you go. Right. And some time interval, you apply that force, going for some change in angular momentum. Now, if it started from rest, then some final, so I times omega. Right. Then, okay, well, what is I for basketball? Again, you wouldn't have to memorize this. If AP had you solve this, which I guess this could be a fair question, right? They would have to give you, let's say for basketball, it'd be 2/3 mr squared. So they would tell you that, right? Rotating about its, again, this is about its central axis as drawn in the picture, right? Not rolling on the floor. Rolling on the floor is like 5/3, but about its central axis like 2/3. Right. Okay, well, now you have enough information you can solve for omega. Like all these posters are solved in terms of variables, but they might give you numerical values. Maybe you have some numbers you can plug in. Okay. Right. We applied a 50 Newton force for 1/10 of a second, and the mass of the ball is however many kilograms the mass of the basketball is at how many meters radius is the basketball. Okay. All right. How about rolling downhill? Rolling downhill. I've got two posters for rolling downhill. Different perspectives, and maybe they're trying to answer the same question. What's the linear speed of? I picked a basketball again, right? Like a spherical shell, right? What's the linear speed of the basketball at the end, right? Now, both of these methods give, of course, the same answer, right? But they're completely different paths through the forest to get to that answer, right? So here's maybe like the more difficult way to do it is through a free body diagram with forces and torques, right? So you could say, here's three forces on this basketball. And notice that I have them at the correct locations too. So the weight I'm drawing is acting through the center mass. That's fine, right? But the normal force and the friction force, I'm not actually drawing at the center mass, right? Which you do like for units 1 through 6 is okay, but unit 7, maybe you want to draw the forces at the correct locations because now there's different forces at different locations on the object, which is setting up a torque, right? So the normal force and the friction force actually act at the surface, right? So now we got a torque going on, right? I might think of it as like, let's see. I know the normal force is going to cancel out with mg cosine theta. So there's an mg sine theta that's providing like a net force. If I ignore the friction, okay, and the friction's pulled back the other way. Right? So relative to this pivot point, I got, maybe I should say it that way. Right? Mg sine theta here. So here's mg sine theta, and then multiplied by r, right? Because like this r right here is acting out, right? Could set up a torque relative to this pivot point. Okay. Then you can, well, here, I know we're getting short on time, so make a series of substitutions and figure out what the speed of basketball at the bottom, right? Let me go ahead and switch to this other poster. All right, here's a different method that results in the same answer. I think this is the easier way to do it, conservation of energy. Because what kind of energy does the basketball have at the top of the hill? Potential energy, mgh, bam, right there. And at the bottom, it has two types of energy. It has your linear kinetic, 1/2 mv squared, but also your rotational kinetic, 1/2 I omega squared. Notice it's okay with this particular method to have the ball rotating about its own center mass, right? Which is not exactly true for the 3-body diagram method. I've got 5/3 mr squared here. I've got 2/3 mr squared here. That's okay, right? And then there's a connection between this v and this omega. You guys remember omega is equal to v divided by r? You do a substitution. So you can solve it. You can get what's the speed of, say, like a rolling object bottom of the hill. Right. And finally, last slide. If you have a roll race, you got all these objects. Right? I have one frictionless lane with an air hockey puck. That's going to beat everything. And then I have a coefficient of static friction for all these other ones. Notice I'm specifying static friction because if it was kinetic friction, it would be like slipping as it's rolling. So static, there's no slipping. A lot of times they'll specify that. Say rolling without slipping, rolling without sliding. Right? You know, all these objects might be completely different masses. That's okay. They'll still finish in this order because of certain distribution of mass. Right? The bowling ball has its mass distributed closest to its center for all these 4 objects, rolling objects. The ring has its mass distributed furthest away from the center for all these comparative objects. Right? So yeah, so they'll finish the race in that particular order. All right. Okay, so that's bringing us to the end of class right there. Got 10 seconds to the bell. What are you guys going to bring to class tomorrow? Laptop. All right. You guys have a good Tuesday, and I'll see you guys tomorrow morning.